So good morning. Okay, this is the Sacco River Valley. It's in Italy. And since the beginning of the 20th century, the town of Colleferro in the valley has been an industrial area with production of explosive, rail coaches, and chemical substances. As you can see from the small map on the left, it's in the Lazio region, 50 kilometers east of Rome, and takes name from the river, of course, the Sacco River. And on the red circle, you can see where the industrial area is. Okay, in 1990, they found what you see in the picture, uncontrolled landfills of industrial wastes in the main industrial factory. And of course, when they checked the water and the soil, they found that there was a problem of pollution. But going to what I'm going to present today, in March 2005, they ran a random sample and national level, and they find very high levels of Beta-Hexachlorocycloexane, that from now on I will call beta for sake of simplicity, in crude milk of a bovine factory in the Sacco Valley. And after other controls, they found out that there was the contamination spread over the valley. And it took a few months later, 30 dead cows found in the river to start to do actually something. And between 2010 and 2015, 2 biomonitoring campaigns were run. Blood samples were collected for 740 subjects. The sample was stratified by sex, age, and area or residence. And together with that, a face-to-face interview was collected with information on several aspects. Okay, beta-HCH is a persistent organochlorine compound, a subproduct of lindane. It's been produced for several years. The factory responsible for that was the SNIA. They produce pesticides. And of course, many studies showed relationship between this compound and several health effects. Unfortunately, when they used this data to try to estimate the health effects, they didn't find much because of the statistical power. But a few months ago, we managed to receive 20 or 30 years of residential court history for all these municipalities. And so men much wiser than me, not me, thought about why don't we use the people we collect blood samples from as monitoring sites, as we do when we estimate air pollution distribution. That is my field of research. And we try to estimate a special distribution of the beta in the valley, and then we apply that, we use that for the general population, and maybe we will find something. And my first reaction was, okay, if we have to do that, we need some methodology allowing to take into account both the spatial dependence, but also the individual informations, because that's where we will take more information from. And we came up with this idea, the integrated nested Laplace approximation. This is a methodology that is quite consolidated, quite used in epidemiology, in other fields of research, as an example in air pollution. And with the stochastic partial differential equation. In few words, the INLA, as we call it, it works in the Bayesian environment, and it's less computationally intensive, much less computationally intensive than the usual Markov chain Monte Carlo algorithms. And the SPDE is, but we have a continuous phenomenon, like the beta concentration in the valley, let's say a Gaussian field, and we are able to have a discrete estimate of the phenomenon, again, with few computational problems. And what we need to do that, how do we do that? With a mesh, and the mesh is a mesh. So it's a triangulation of the space. And you just have to decide how small the triangles will be, because the smallest, the finer the estimates, but of course, the more complex the model. But I will show you later, in a few minutes, how this works. So our population was the 740 subjects in 7 municipalities. Well, in this model, of course, that is the outcome, not the exposure. We used the beta on the log scale after looking at the distribution that was skewed. And these were the covariates that we used. And that's because since we were thinking of using these estimates on the general population, we only use those variables that we will be able to have for the general population. So age, gender, distance from the river, and altitude, which is quite important because the valley is, the river is the lower point, and then it goes up with valleys and hills and also mountains. And since we wanted to use all we could, we added the census tract socioeconomic level and the core-inland cover. And after removing 25 subjects with missing values and 20 outliers, and I will show you why, we ended up with more or less 700 subjects. Okay, these are our points. As you can see, the river is in the middle, going from west to east. The red dots are the one with the higher concentrations. And of course, we found concentrations much higher than on the average population. And on the upper right part, you see points in red circles. These are the ones that we eliminated. We erased it from the analysis because it's really hard to estimate a spatial distribution with so few points, and mainly because the interest is on the area along the river. So this was the core-inland cover map. All the areas that you see in green or something like green are green, so we just ended up with 3 values: residential, industrial, and green. And this is the socioeconomic level in 4 levels. So before even starting, we said, OK, let's see if it's true there is a spatial component in the model. So first of all, we also run a linear regression with the beta and latitude and longitude, and both the coefficients were significant. Then we used the experimental variogram and the Moran index. And all these tests told us that, yes, there is a spatial component. So next step was, how do we build the mesh? How do we define the area that we are interested in? Looking at our points, we decided to define 3 clusters. And first of all, we designed the yellow areas, the convex hulls, around our points. And we tried to fit the model, and it didn't work. So we tried to extend the area to the orange part, and then we arrived to the red part, and that was the best fit. And what we got is the mesh. This is the mesh. And so as you see, in the area that we defined, the triangles are smaller, giving us better, hopefully better estimation. And then we design another area with bigger triangles, so it means we will have less power there. As you will see, the estimate there is almost constant, but again, we won't use that. We are not interested in that part of the valley, let's say. And these are the coefficients we got from the model and what we expected. So higher levels in females, increasing higher levels of beta with increasing age. You have lower levels if you get far from the river, and if you get higher, which more or less are the same. And after we control for all these variables, longitude and latitude didn't have any effect. And again, on the socioeconomic level and on the core-inland cover, I won't discuss, but believe me, these coefficients were what we expected. And this is the map. we obtain. This is the spatial prediction. As you can see on the right, there is a kind of a agenda with the values. And that values, first of all, we are on the log scale. And secondly, these are for the, let's say, the average subject. We estimated those values. So this is the map for a man of 44 years of age, and so on. Of course, this is only an example to let you understand the variability. And as you can see, all the variability is along the river. And the red areas are the one more with higher concentrations. OK, how did we validate the model? This is our area with the river and the points. We ran a tenfold cross validation. And we just added a little trick, and the red points are one of the examples. We constrained the cross validation for the training and the testing sample to have a similar spatial distribution. So it was not completely random. We just used this trick, but it didn't change much, actually. And the correlation was 0.78, which to me was impressive, since what we are doing. And then we ran a sensitivity analysis. We took from the interview I was talking about before, we took the variables that were highly correlated to the beta levels. And these variables were, do you wash yourself with water from private wells? Do you drink that water? Do you eat local food? And maybe you live far from the river, but you use the land next to the river, or you own that for pasture, because most of the people living there are farmers. And again, the coefficients are all high, almost all significant, again, as we expected. And if we put that information in the model, the correlation jumps to 0.88. But again, the problem is, how do we use these estimates, since we don't know these for all the people we want to put in the final analysis? So if you have any idea, please share it. So in conclusion, the methodology is tricky, but it's been used for several years. It's plenty of tutorials. By the way, all the analysis was run in R. And if you go to the INLA site, it will take a while, but you manage how to do it. And we were able to keep into account both the spatial component and the individual covariates. And the model had a good accuracy, again, because of what we are trying to do. And one of the most important things I didn't show you because I forgot to, but together with the map of the prediction comes a map of the uncertainty. And this means that when you will estimate the effects, the health effects, you will be able to translate that uncertainty into the final estimates. So it won't be like you have a point estimate and that is the true exposure. You're taking into account the fact that you are estimating the exposure. It is not true, and it is really important to remember that. It is not true, at least it is not observed. The limitation, that the biggest one, is we're still not sure if it makes any sense, what we are doing. So this is why we are here. Thank you. That's it.